Hello everyone, this is part 5 video on past year NEET questions from the chapter thermal properties of matter. Now those who are looking at this video, right, can also take a look at the previous 4 parts so that you will have the continuity of questions. We'll start with a question that has come in the year 1995. This is a question based on the Newton's law of cooling. A beaker full of hot water is kept in the room. If it cools from 80 to 75 in time t1 minutes, 75 to 70 in time t2 minutes, and 70 to 65 in time t3 minutes, then we have to look at what will be the relation between t1, t2 and t3. So obviously if you look at it right, here we have 3 cases, case 1, case 2 and case 3. What is the case 1? The temperature is decreasing from 80 to 75, means it is a drop of 5 degrees Celsius. Second case, from 75 it is decreasing up to 70, means again here also what is the drop of 5. Third case also interesting. What is it? From 70 it is becoming towards 65, means here also what is the drop? 5 degrees Celsius. Here the time taken is t1, here it is t2, here it is t3. What is the rate of cooling here? Average rate of cooling is what? 5 divided by t1, 5 divided by t2. Here it is what? 5 divided by t3. That is the average rate of cooling. So whatever the temperature drop divided by the time taken. Now as per the Newton's law of cooling, right, the rate of cooling. So rate of cooling is basically whatever is the temperature drop divided by the time taken. So we'll generally represent it as what? Minus delta theta by delta t. So minus will come because, so here we'll actually, cooling means what? From high temperature, initial temperature will be high and final temperature will be less. Delta means what? Always we will do final minus initial, right? That's why we have to put minus. So the rate of cooling minus delta theta by delta t will be directly proportional to what? Theta average of the body minus theta ambient or surroundings. So that is what is the relation we have. Okay, so here we can even put it like, this will be equal to a constant C into the average temperature of the body minus the ambient temperature or the surrounding temperature. So here they have not given us what is the average temperature and they have not given us what is the ambient temperature. So average temperature means what? How do you find average temperature? In case 1, the temperature is changing from 80 to 75, right, for that object. So what is the average of them? Means 80 plus 75 by 2, which is what? 77.5. Here what is the average temperature? Means 75 plus 70 by 2, it will be what? 72.5. Here what is the average? 70 plus 65 by 2 means it is what? 67.5. Okay, so that is the average temperature. So ambient temperature they have not given us, so let us just take it as what? 30 degrees. Now we'll proceed and then write down the expression in all the 3 cases. So this rate of cooling already we have. In the first case it is what? 5 by t1. Second case it is what? 5 by t2. Third case it is what? 5 by t3. That is the rate of cooling. The temperature drop. That formula actually minus delta theta means what? Temperature drop, because it is the case of cooling. Okay, so minus delta theta by time. These are the rate of cooling. So look at it. In the first case, what is it? 5 by t1 is equal to what? A constant C into the temperature difference between the object, which is the average temperature of the body, minus surrounding temperature. We said surrounding temperature, we'll take it as what? 30. So 77.5 minus 30 means what? It is 47.5. Here what is the equation? 5 by t2 will be equal to what? C into 72.5 minus 30 means what? It is 42.5 will come. Here what will be the relation? We'll have what? 5 by t3 is equal to what? C into, this is 67.5 minus 30 means what? It will be 37.5. So from here we will be able to conclude what? So we can give the values. T1 will be equal to what? If you rearrange means what will be T1? 5 by C into 47.5. T2 will be what? 5 by C into 42.5. Similarly T3 will be what? 5 by C into 37.5. See, this problem we could have concluded the answer without even really getting these final expressions, because when you look at in each of the cases the temperature drop is same, means the time taken will depend upon what? The temperature difference between the object and the surroundings. So wherever the temperature difference is more, obviously in first case temperature difference will be more. In that case, rate of cooling is faster. Rate of cooling is faster means what? The time taken will be less. Like that we could have concluded the answer by looking at the temperature drop being same. But if you have a different question, right, where the temperature drop values are also different, then this is how we actually have to proceed. Like this, we have to get the final expressions for T1, T2. Now we can see, right, in all the cases 5 by C is common. What is changing? Only denominator. In T1 case we have 47.5, T2 case we have 42.5, T3 case we have 37.5. So wherever the denominator is high, the corresponding time will be what? Least. So 47.5 means the time will be least. So what is the order? T1 is going to be less than T2, less than T3. So what is the answer for this? Option A will be the answer. Again, this problem we could have solved without even really getting these expressions. Now you may think, will the assumption we have taken, the ambient temperature to be 30, is it going to play a role? It will not play a role. The temperature difference, right, even if you would have taken the ambient temperature as what? 25, the temperature difference will be maximum in the first case only, and it will be minimum in the third case, because whatever the ambient temperature we take, right, temperature difference will be maximum in the first case and least in the third case. So that is not going to change our order of these T1, T2, T3. Okay, so what is the answer for this? It is option A. We'll move on to the next question. This is come in the year 95. This is based on thermal conductivity. Heat is flowing through two cylindrical rods of same material. Means what? The coefficient of thermal conductivity for these materials will be what? Same, because they are made up of same material. The diameters of the rods are in the ratio 1:2. Means if you take say for example rod 1 and rod 2, what is the ratio of the diameters? What do we have? Let's say here it is D1, here it is D2. D1 by D2 is what? It is 1/2. Then the ratio of the lengths is what? 2:1. So here length is L1, here it is L2. So ratio of the lengths means what? L1 by L2 is what? 2:1. If the temperature difference between the ends for both the rods, the temperature difference is what? Same. Delta T here, delta T here. And also since they are made up of same material, the thermal conductivity value also will be same. Let us say this is K. Then the ratio of rate of flow of heat through them will be how much? We need to find what? The ratio of rate of flow of heat through these rods will be how much? Okay, so if you look at what is the rate of flow of heat, right? What is the rate of flow of heat formula? If you call the rate of flow of heat as, say for example R, it will be equal to what? K A into delta T by L. So in this case, what do we see? For both these rods, if we are comparing, means the K value is same, delta T is also same. Now what do we see? The rate of heat flow is directly proportional to what? Is directly proportional to A by L. Okay, so here what we will be able to see is that if you look at R1 by R2, that will be equal to what? A1 by A2 into L2 by L1, because directly proportional to the area and inversely proportional to what? Length. So what is the R1 by R2? It will be equal to what? A1 by A2 into L2 by L1. Now if you consider the rod to be cylindrical, right, area will be equal to what? Pi into d square by 4, the area related to the diameter, because they are giving us the relation in terms of diameter, right? Means what? A1 by A2 will be equal to what? D1 square by D2 square. Ratio of the area will be what? D1 square by D2 square. Means here we can see D1 by D2 is what? 1/2. So A1 by A2 will be what? It will be 1/2. I'll just erase some part of it so that we can use the space. So A1 by A2 will be what? A1 by A2 will be D1 square by D2 square, means what? D1 by D2 the whole square, which is what? D1 by D2 is half, so 1/2 square will come. And they have given us L1 by L2. L1 by L2 is 2:1. But here we'll have L2 by L1, right? L2 by L1 means what? It will be 1 by 2. Okay. So look at this one more time carefully. R1 by R2 is equal to what? A2 by A1, which is D1 by D2 the whole square. Okay, so D1 by 2 is 1 by 2, so 1 by 2 the whole square will come. Into L2 by L1. The ratio of the lengths is 2:1, right? So L1 by L2 is 2:1. So L2 by L1 means 1:2. So you can see here 1 by 2 square means what? This is 1 by 4 into 1 by 2. Totally what is it? 1 by 8 will come. So that is the ratio of the rate of flow of heat through these rods. So what is the correct answer for this? It is option D. So like this, the ratio based questions, right, are quite important when it comes to the rate of conduction. Like we have these variables, right? The coefficient of thermal conductivity is one variable, area is a variable, temperature difference is a variable, length is a variable. They can ask these kind of ratio based questions by changing the values of the variables. Okay. Next we will go to a question that has come in the year 1993. If the temperature of the sun is doubled, the rate of energy received on the earth will be increased by a factor of. So what is it? I mean, so this diagram is just to tell that sun is like, a very hot balloon of, gas, which will be undergoing constant fusion, and the fusion is what will be giving us the heat. So when the sun is radiating, right, it will follow the Stephen's law of radiation. What is it? The radiation power. So radiation power that is emitted by the sun will be directly proportional to what? Fourth power of temperature of the sun. Okay, so if the temperature of the sun, but of course, here we should take the temperature on the Kelvin scale, that we should keep in mind. If the temperature of the sun is doubled, means, they are doubling the temperature, which means what? The final radiation power by initial radiation power will be equal to what? Final temperature is twice, right? So it will be 2t power 4 divided by t power 4, which means what? The 2 power 4 will be remaining, t power 4 is cancelled. So what is it? 2 power 4. 2 power 4 means what? It will be 16. So the final radiation power will be equal to what? It will be 16 times of the initial radiation power, which means what is the answer? The answer is option D. The radiation power will be increased by what? 16 times, which means the radiation is what is giving the energy to the earth, right? When the radiation power emitted by the sun is increasing 16 times, means the rate of energy received on the earth also will be increasing by 16 times. Okay. Next we have a conceptual question based on the mercury thermometer. So this has come in the year 1992. Mercury thermometer can be used to measure temperatures up to. So people will be thinking, what is this question all about? So we know that mercury thermometer, it basically works on which principle? It works on the principle of volume expansion of mercury. So when the mercury is heated, it will increase its volume, and the volume expansion is what is the basic underlying principle for the working of the thermometer. So we will see that the expanding mercury will be able to show us appropriately what is the reading value for the corresponding temperature. Okay, but the thing is, the mercury thermometer will work as long as the mercury is in the liquid state. So if you look at the two temperatures, one is the boiling point, where the mercury essentially will get converted into vapor. So boiling point of mercury is nearly 356.7 degrees Celsius, and the other side is freezing point, where it will solidify. So freezing point will be minus 30 degrees Celsius, minus 38, okay, to be more appropriate. So which means what? The operating range where we will require the Hg to be in the liquid state, right? The operating range we will say broadly is what? Between these two temperatures, the freezing point and the boiling point. So what we will say is, so look at what is the temperature that is really close to this 356 or 357, that is 360. So we are looking at up to, means we are looking at the upper limit. So what is the upper limit we can take? We can take it as what? Nearly 360. Lower limit we can fix it close to minus 30, somewhere around that. Okay, so since the freezing point is minus 38, we should have the operating range in that particular value. So this is about the operating range of the mercury thermometer. Operating range essentially is what? The temperature range where we'll have the mercury in the liquid state predominantly. Okay, next we have a question. This is about temperature conversion. This has come in the year 1990. A centigrade and a Fahrenheit thermometer are dipped in boiling water. Means what? So we have boiling water and we are dipping both centigrade and Fahrenheit thermometer. So centigrade will show how much reading. When you dip into boiling water means it will show 100. Fahrenheit will show how much? It will be showing 212 degree Fahrenheit. So that is the reading that we'll have for the boiling water, right, on both the scales. The water temperature is lowered until the Fahrenheit thermometer is resisting 140. Means what? The reading on the Fahrenheit scale is what? 140. What is the fall in temperature as registered by the centigrade thermometer? See, Fahrenheit is coming down from where? 212 to 140. We need to look at what is the drop that you will see on the Celsius scale. Basically, we need to find what is the corresponding reading on the Celsius scale. If the Fahrenheit thermometer is showing 140, right? What is the corresponding reading on the Celsius scale? That we should find. So how do we find it? If you look at the temperature scales, right? Here we have the reference temperatures. For Celsius scale, reference temperatures are what? The melting point of ice, which is 0, and boiling point of water is 100. Fahrenheit, melting point of ice is what? 32. Boiling point of water is 212. Any temperature you take on Fahrenheit scale, let us say degree Fahrenheit, the corresponding temperature on Celsius scale, degree Celsius. The relative distance traveled, this is the relation. Relative distance traveled means what? The distance traveled on the Celsius scale, or the length covered on Celsius scale, divided by total length of the scale. Between 0 to 100 means what? It is 100. That will be equal to the relative length covered on Fahrenheit scale. Means what? Whatever is the Fahrenheit reading minus initial reading is what? 32. Divide by what is the total length of the Fahrenheit scale means 212 minus 32, it is what? 180. This is a very standard relation that we'll remember. So I'm just trying to explain to you guys one more time, but some of us will already know this relation. Okay, so what is the concept? The concept is relative distance covered on any temperature scale must be same. That is the basic principle of this conversion. So here you see Fahrenheit temperature is given to us. What is it? 140. So look at this, degree Celsius by 100 is equal to what? 140 minus 32 by 180. 140 minus 32 means what? That is 108. 108 by 180. So we can see here 10 tens are 10 18s. 18 ones are 18 sixes. Which means what? We'll take the 10 to the right side, it will go to the numerator. So what we have is the corresponding degree Celsius value will be 6 into 10, that is actually 60. So Celsius scale reading is what? 60 degrees. But here we have to be careful. They are not asking us what is the temperature that is shown by the centigrade thermometer. What they are asking, what is the fall in the temperature as resisted by the centigrade thermometer? Means they are asking what is the fall. Fall means what? From 100 it is coming to 60, means by how much it is falling? It is falling by 100 minus 60, which is going to be what? 40. Some of us, having done the entire calculation right, will mistakenly just go and tick option B and move on, because we have to be careful while reading the statements. What they are saying, they are not asking us to give what is the temperature reading on the centigrade scale. They are asking us what? Give us the fall in the temperature as it is shown in the centigrade thermometer. Okay. Next we have a straightforward theoretical question which is based on the thermal capacity. Thermal capacity is also called as what? Sometimes heat capacity. Okay, thermal capacity can be also called as what? Heat capacity. Thermal capacity of 40 grams of aluminum. For the aluminum, right, they have given S. S means what? S is what? Specific heat capacity. So thermal capacity, or the total heat capacity, which we generally represent by the symbol capital C, will be equal to what? Mass of that particular object into its specific heat capacity. So what is the mass of the object? It is 40 grams, right? Into specific heat capacity is what? It's a straightforward question. 2 calorie per gram. So gram will be cancelled. What is it? 40 into 0.2 means it is 8 calories per Kelvin. But if you look at these options, right, they are not giving in terms of calorie per Kelvin, but rather they are giving in terms of what? Joule per Kelvin. So what we'll do? We'll just use the conversion factor, right? 1 calorie is equal to what? 4.2 joules. 1 calorie is equal to what? 4.2. Now look at it. 8 2s are 16, 8 4 32. Means what? 33.6 joule per Kelvin. So where is our option? It is option D. It's a straight question. Just that total heat capacity of any object is equal to what? Mass of that particular object into the specific heat capacity of the material by which this object is made up of. Okay. Next we have an interesting question which is based on the calorimetry. This has come in the year 1988. 10 grams of ice cubes which are at 0 degrees Celsius are released into a tumbler. So tumbler water equivalent. Water equivalent means what? Any substance, if we don't know what is the specific heat capacity of the substance, we want to understand the behavior of that substance in thermodynamics or with regard to the heat changes. Then we can sometimes replace that object with what we call as water equivalent. Means here when we say the water equivalent of the substance is 55 grams, means in the heat calculations we can replace the tumbler by what? The tumbler can be replaced by 55 grams of water. That is the concept of water equivalent. So we are releasing these ice cubes into a tumbler whose water equivalent is 55 grams. Means the tumbler in terms of our heat calculations is equal to what? It's simply equal to 55 grams of water, like that. The tumbler is initially at what temperature? 40. Assuming that negligible heat is taken from the surroundings, the temperature of the water in the tumbler becomes nearly equal to, they are giving us L. L represents what? Latent heat. So here this will be what? The latent heat of the fusion or melting for the ice. So look at it. What is the situation here? So we have the tumbler. So this is the tumbler. Okay. We are putting these ice cubes into the tumbler. How much is the mass? 10 grams. These ice cubes are at how much temperature? 0. Tumbler is at what temperature? 40. So what is going to happen? The tumbler is going to lose heat because it is at high temperature, and the ice will start gaining heat. So first ice at 0 has to melt. So for ice, right, the heat change will result in what? First melting. Then it can increase the temperature. First it has to fully melt. Then it can increase the temperature. What about the case of the tumbler? Tumbler temperature is going to decrease. Why? Because since it is at high temperature, it will lose heat, so its temperature will decrease. Let us say both of them come to a common temperature T finally. That is what is the equilibrium temperature. That is in fact what they are asking. Now in this process, right, what is going to happen is, whatever is the heat that is lost by the tumbler is going to lose heat. That will be equal to what? Heat gained by the ice. So ice will gain heat while it is melting, and it will also gain heat while it is increasing temperature. Once the ice is melting, means it becomes water, liquid state. Then it will start increasing the temperature. So first fully the ice will melt. So if you have 10 grams of ice, right, means what is the heat required for melting? So for the melting of ice, what is the heat required? It will be equal to what? Mass of that ice into latent heat, which is what? Here it is 10 grams into 80 calories per gram. That is what? It will be 800 calories. Okay, so that is what is the heat required for the melting. And then if it is finally coming to temperature T, means now this is molten, means it is in the liquid state. So from 0 it is going up to temperature T means what? The heat required for this temperature change is what? Ms delta T, right? Which means what? M is the mass, which is 10 into specific heat capacity of water is 1 calorie per gram per Kelvin or 1 calorie per gram per degree Celsius. So which is what? S is 1 into delta T means what? T minus 0. So to come to that final equilibrium temperature T, what is the total heat that is taken by the ice? This 800 plus the 10 into T. This is the total heat taken by the ice. Now what about the heat lost? The other side, tumbler will be losing the heat. Tumbler is going to lose the heat, right? So heat lost by the tumbler is what? Tumbler will be decreasing its temperature from 40 to T. So the value of T will be, we will get a hint. What is it? The value of T will be between 0 to 40. So tumbler is going to decrease its temperature from where? From 40 to T. Tumbler is equal to what? It is equal to 55 grams of water. That is why we are using the word water equivalent. Means here the heat that is lost by the tumbler is equal to what? Mass, which is 55 into specific heat capacity, because we are equating this tumbler to 55 grams of water. Specific heat capacity is 1 into temperature drop is what? From 40 it is coming to T, means 40 minus T. This is the heat lost. Okay, so whatever is the heat that is absorbed by the ice will be equal to the heat that is lost by the tumbler. So we'll have to equate them and then we'll be able to find out what is the T. That is the basic principle. Okay, so calorimetry is always what? One object or some of the objects will be losing the heat and the others will be gaining the heat. So calorimetry principle is what? Heat lost by the hot objects will be equal to heat gained by the cold objects. Now look at it. For the ice, what is the heat required by the ice? M into L, mass of the ice into L. This is for the melting. And then for raising the temperature from 0 to T, Ms, final temperature is T, initial temperature is 0. So mass is what? 10, L is what? 80, and mass is 10, specific heat capacity is what? 1 calorie. So for the water, what is the S value? 1 calorie per gram per degree Celsius into T. So this is, we can write as what? 800 plus 10T. Okay, now what about the heat that is lost by the water? So when we say water, right, water referring to the tumbler, because we are using the water equivalent concept. Okay, so what is the heat lost by the tumbler, which is what? The mass is because we are saying it is equal to 55 grams of water. So 55 into, again 1 will be coming, so 1 we are just anyway multiplying by 1 means nothing will change, into temperature is coming from where? 40 to T, right, decreasing. So 40 minus T, this is the heat lost by the water. So what is the relation we have? The heat required or heat gain by the ice will be equal to heat lost by the tumbler, means 800 plus 10T is equal to what? 55 into 40 minus T. So we can see what is it? 55 into 40 means what? That is 2200 minus 55T. So if you rearrange means what we are going to get? We'll bring the minus 55T to the left side. So that is what? 10T plus 55T. Right hand side is what? 2200 minus 800. That is actually 1400. So 65T is equal to 1400. So from here, what is the T value we'll get? T will be 1400 by 65. What is the T value? 1400 by 65 will come. Okay. So if you simplify this, we'll be able to get the answer for the T to be approximately 21.54, and 21.54 means what? We can round it off to 22 degrees Celsius. That is the nearest option that is given to us. Okay, so in this, what we did basically, we have looked at the basic principle of calorimetry. The heat lost by the hot object, in this case the tumbler, is equal to what? Heat gained by the cold object, which is the ice. So this is about the part 5 video, and this is in fact the last part of the thermal properties of matter. So with this we have completed the discussion of past year NEET questions on thermal properties of matter. So make sure that you focus on whatever the important types of numericals. Like if you look at the all 5 parts, you will see the radiation power questions, or the questions based on thermal conduction. So these are the areas, along with of course the thermal expansion. So these are the areas where we have seen most of the questions coming from. So we have to make sure that we give more importance while your practice also, like the Stephen's law, Wien's displacement law, and Newton's law of cooling, thermal conductivity relation. So all these things we have to be keeping in mind while doing the practice as well. Okay, so all the best, and we'll see in the next chapter videos.